Well, hello, ladies and gentlemen. We're going to go over the second, the second page of our balancing and types of reaction test review for 2018-19, part 2. I've already done page 1. Let me zoom in here. And we're going to be working on the back page. This will be a lot quicker than that first one. I couldn't believe that was a 30-minute video. Anyway, let's get working here on those. Let me make sure we're zoomed in. So these few right here, you need to be able to predict the types of reactions. Now in a synthesis reaction, you've got two compounds or more joining together into fewer. And the simplest version of this is two compounds are joining into just one type of compound on here. And so if you have something, okay, the hydrogens and the oxygens have to go. The simplest, if you said HO, which is hydroxide, cool, that'd work. If you said H2O or H2, okay, cool. Or if you said H2O2, because we've used that, okay, any of those would be appropriate, but just one of those. Any one of those would be an appropriate answer. Now in the next one, we've got a decomposition reaction, which means we've got, in this case, one compound is breaking, and I've kind of helped it out. We're breaking it into two compounds. So decomposition, this could be into two or even three, but we're giving you a little hint here. And I'm telling you right now that C and O have already formed this compound there. So this over here has to be at least, maybe it's just going to form plain old calcium metal. You don't have to worry about balancing these. Or maybe you said, I think it could be, maybe you said calcium oxide. Okay, that could have been an appropriate answer on there. Or you could have even said, hey, I think it's going to be calcium carbide, CaC. Okay, any one of those would have been appropriate on there. But the idea is that you need to recognize that there's going to be two compounds formed, and you got to make sure that those two compounds have each of the elements that make them up. Zoom out here. Now we're telling you that we've got a single replacement reaction. Now, single replacement reactions and the combustions coming up, these share something in common. There's always going to be two compounds that break down into two compounds. You've got to be able to recognize that pattern. So make sure you've got that pattern down. Better zoom out a little more. Picture. And again, we don't care if you get you don't have to balance the equation on these. Just predict. So up here, we've got a single replacement. My favorite analogy is, here's the dance couple, hydrogen and chlorine out dancing. Magnesium comes along, and it's going to kick off either the metal or the hydrogen. It's always going to kick off the first one in the group. So now we can see in the products, we got hydrogen over here, and the new dance partners, well, chlorine will now be dancing with magnesium. So on the test, what you got to recognize is that you're going to have two compounds. So any choices that have either just one compound or maybe if they have three, you can cross those off right away and then make sure that you've got at least two compounds, and in those two compounds, all three of the chemicals are represented. This is a double replacement. Double replacements, two compounds, form two. And we know it's going to be a double replacement because this metal is going to kick off the silver, or if you like, two dance partners. And the sodium's going to come over and say, hey, I'm going to dance with the nitrate. So you should expect that sodium will have a new dance partner, in this case NO3. And let's see, silver got kicked out, so silver is going to say, hey, I'm going to go team up sodium with your old dance partner. So we should have silver and chlorine. That is what we should expect on those. So if you can, let me scoot that over so you can see there a little better. Now with combustion, if we tell you it's combustion, you had just better expect, because combustion is the fancy name for burning, you're going to get CO2 and water. Done. Okay? So you just got to recognize that oxygen with a hydrocarbon is going to produce CO2 and water if it's perfectly burned. Why is it easier to mix cocoa and hot water than cold? Draw a diagram model. Well, if you've got a cup of hot water over here, this is hot. Let me make sure you can see that I didn't go off the page here. Okay, the water molecules in there, I'm going to draw them with circles. They have high kinetic energy. They are moving fast. So this is the water molecules going quick. So if you've got a little chunk of some crystal in their hot cocoa mix, this hot cocoa mix is going to be hit often by these water molecules, and since they're moving faster, they're going to have more energy. And so because you've got more collisions, you're going to get more collisions with the hot, collisions, okay, collisions, sorry about that. The more collisions you get with more energy, the quicker that little piece of sugar or compound is going to be worn away. Cold, the molecules are really slow, and it comes down to there's fewer collisions. The compounds are hitting that little dissolved chunk way fewer times with much less energy, so it's going to take a lot longer to break that apart when you've got really low kinetic energy, which means they're not going fast. Over here, this is just going like crazy. Almost immediately, it starts dissolving this away because there's so much energy in there. Over here, it's a slow process. Let's see here. I think we did all that. Number 19. Let's go back to our question there. Better zoom out so we get the whole. Why does rock salt, oh, and I hope I did I misspell dissolve? D-S-S-O-L-V. I think I got that. I'll have to fix that. Sorry. But anyway, why does it take rock salt longer than little tiny crystals of salt, little salt crystals? So a big chunk, why does this take longer? This takes longer to dissolve. This takes a shorter time. And the reason for that is, we went over in class that when you have this huge crystal, when you have the water medium or the reactants hitting it, there is so much inside of it that it takes so much longer for these compounds, for the water or the reactants to reach there, that by the time these little tiny ones, you don't need many collisions to dissolve this little tiny one. Within almost no time at all, it's broken down. Because here we've got a very low, what we call surface to volume ratio. Okay, this may be really big, but when you compare how big the inside is to the outside, it's a really small value. These little crystals, even though they're super tiny, their surface area, they have a high, actually what I should do is do this on this one, really small surface, huge volume. These guys over here have a high surface to volume ratio, which means this, the surface is huge, the volume is tiny, so there's more surface area for the volume. Very quickly, the collisions of molecules break it down. So it really comes down to, you've got more, even though these are smaller, they've got more surface for their size. These guys, even though they're huge crystals, they have a really low surface area compared to their volume. So that anytime you grind something up, it'll react quicker. Number 20. Why does cocoa mix stir faster? Why does it dissolve faster when stirred? Well, when you stir it, you're increasing. I'm going to draw the water particles. They've got increased kinetic energy. You're making them go faster and more crystals. It's kind of, in a way, it's almost like you're doing the same thing we did with the heating it up. You're increasing the kinetic energy. You're going to get more collisions. And the more collisions of particles you get, the quicker that little chunk of dissolved stuff can break down. If you don't stir it, okay, those water molecules are barely moving. I mean, they are moving slightly, but it's going to take, there's few collisions of molecule. So if you stir it by putting in that spoon in there, okay, there's my spoon right here, stirring that, you're increasing the collisions, increasing the kinetic energy, and it's going to break down quicker. So 21 is about catalysts, and catalysts are one of the ways you can make a reaction go quicker, and they help a reaction occur. A catalyst helps a reaction, I'm going to abbreviate reaction, go faster. They're not used in the end result, and my favorite example is scissors. Because if you have, let's say, a piece of paper and you're going to have to cut it into a whole bunch of little tiny pieces. If you've got a pair of scissors handy, those scissors can make you end up with a whole bunch of really nicely little tiny pieces here. Now you're not going to, if you start with one piece of paper and the scissors, you're not going to end up with more paper over here. You're going to end up with a whole bunch of little pieces, but you're going to end up with the same mass of paper. And when you're done, the scissors are untouched, and that's what makes them a catalyst, because catalysts are not used in a chemical reaction. They let it go faster, but they're unused. And you can even, a lot of times in industry, they'll recover the catalysts and then put them back in with the reactants. So looking at this chart over here, and you need to be able to interpret charts and such, how much energy does the uncatalyzed reaction need? Well, we've got a chart here with energy over there. And we've got, no, sorry for the reaction coordinate, we can just say time. That's what I should have put there. But how much energy does the uncatalyzed? Here's the uncatalyzed reaction. Well, here's the top of it, because here's the products, and you've got to always add usually some type of energy to the products. A lot of times it might be heat or whatever, but in this case, we've got to add around 300 joules of energy to get this one. So how much energy does this one need? About 300 joules of energy. How much energy does the catalyzed reaction? So here's the catalyzed one. You notice the graph is lower, and which means if we come over here, it only takes about 250 joules of energy to get the reaction going. So much less. So this may be, if you're working in a factory or something, and you found normally you would heat up the stuff. If you can add a catalyst, you may not have to heat it up as much, and you won't have to pay as much for electricity. And with both of these reactions down here, the products always end up the same. So we're going to have the same number of products over here. We didn't get more, we didn't get less. We just got them a lot. They're going to get them with less energy, and often it's going to be a lot faster. And how much energy does the catalyst save? Well, let's see, 300 minus 250 joules is around 50 joules, is how much the catalyst would save us. All right, so that's most of those, and then let's see, the last one is that I wanted you to get prepared for our next unit. So we need to be able to know how many how many atoms there are in each of these molecules, and I want you to be able to figure out their molecular weights. And when we take a look at this, okay, since there is no subscript 1 after the silver, we've got just 1 silver. Nitrogens, okay, there's the subscript 1. There's no number outside the parentheses, so that would just be like 1. So there's just 1 nitrogen. Oxygens, okay, there's 3 oxygens inside of the parentheses, and there's 3 oxygens. The 3 tells us we got 3 of those. And since out here there's just a 1, 3 times 1 is just going to be 3 oxygens. And now let's see, now for the second part, that's how many atoms of each, the molecular mass. The silver weighs 108, and there's only 1 of those, so 1 times 108. Plus, we've only got 1 nitrogen, so, I should be consistent. Okay, I'm going to put the parentheses around the numbers instead of their weights. Nitrogen weighs 14. Plus, we've got 3 oxygens, and when you look on the periodic table, they weigh 16. And so we've got 108 plus 14, that's a parenthesis. 3 times 16 is 48. I'll let you add that up yourself. I'm going to zoom in a little bit more here so we can see that on your phones a little bit better. So it's going to be 108 plus 14 plus 48. You do the math. I'm not going to. Hydrogen peroxide, we've got 2 hydrogens and we've got 2 oxygens, because the subscripts tell us how many of those we have, how many of the atoms in front of them. And let's see, we're done with the first part of the question. How heavy is it? We've got 2 hydrogens. They each weigh 1. Because if you need to, you look on a periodic table, and hydrogen has a mass of 1.01. We round it to the nearest whole number. Plus 2 times oxygen weighs 16. So when we add these up, we're going to do 2 times 16 is 32 plus 2. You can get your own math there. Okay, we got adenine here, one of the nitrogenous bases of DNA. It looks like we've got the 5 tells us there's 5 carbons. There's 5 hydrogens as well. Oh, wow, and we've got 5 nitrogens. That's interesting. Now for the second part, how heavy they are. So we've got 5 carbons over here. Each carbon weighs 12. Plus we've got 5 hydrogens. Each one weighs 1. Plus we've got 5 nitrogens. Each one of those weighs 14. So when you go through and do your math on that, let's see, 5 times 12 is 60. These are atomic mass units, by the way, but I should have atomic mass units. So we're going to have, let's see, 60 plus 5 plus, see, 5 times 14 is 70, if I did my math right, make sure. You can add those up yourselves. And lastly, cytosine, just for practice, it looks like we've got 4 carbons, 5 hydrogens, 3 nitrogens, and if there's not a number afterwards, that means there's just one of them. So when we go to do this, we're going to do, there's how many atoms of each. Now we're going to do the molecular weight of this compound. 4 carbons at 12 each, plus 5 hydrogens, each one weighs 1, plus we've got 3 nitrogens that each weigh, should have put the parenthesis, there we go, weighs 14, plus we've got only 1 oxygen weighing 16. So when you go to add those up, we're going to have for the carbons, 4 times 12 is going to be 60, and then we've got 5 for the hydrogens, and I think this is going to be 42 for the total weight of all the nitrogens, and 16, and you can add them up yourself. All right, there you go. I would recommend you practice these. Take a look at chemical equations that you have already labeled as what their types are, cover up the products and practice it, and also practice balancing your equations. We won't give you one as hard as number 6. They'll be much easier. Goodbye.